Welcome to the Explainer. Today, we're diving deep into the AGI Solver. We're going to explore a really rigorous technical overview of a proposed symbolic reasoning architecture. It's a system specifically designed to tackle incredibly complex abstraction tasks using things like program synthesis, hypothesis competition, and exact verification. Let's just jump right in. So, here is the central question we're looking at today. For years, we've seen AI systems that absolutely excel at recognizing statistical patterns. But true reasoning, that requires something a lot deeper. Today, we're taking a journey from raw, unstructured pixels all the way up to machine-readable reasoning. The big question is, can a system actually discover the underlying rule, the actual why behind a visual transformation? Here's a quick look at our agenda for today. We'll start with the abstract reasoning challenge, look at the transition from pixels to objects, explore the GLYPHBLOCK engine, dive into program synthesis, check out the exact verification gate, and finally wrap up with how this achieves true generalization. All right, let's start with section 1, the abstract reasoning challenge, and how we move beyond simple pattern matching. If you're familiar with the abstraction and reasoning corpus, or ARC, you know it tests generalization from just a tiny handful of examples. And notice the stark contrast here between superficial memorization and true logical reasoning. A system gets a couple of input and output grids, and it has to figure out the underlying transformation rule to solve a totally unseen test grid. You can't just memorize your way out of this. Success demands that the system shifts its entire approach from asking, "Have I seen something like this before?" to asking, "What abstract transformation actually explains these examples? And can I use it in a brand new situation?" Moving on to section 2, from pixels to objects, or what we call the pixel to symbol problem. Okay, so here is the fundamental architectural shift that's required for actual reasoning. Think about a raw grid for a second. Colored pixels by themselves contain practically zero explicit semantic meaning. A reasoning system has to do all the heavy lifting. It has to figure out which pixels belong together, what even makes an object, and what relationships exist between those objects. So the data literally has to be transformed. It flows from raw pixels to distinct objects to relations and finally into abstract concepts. To do this, the system extracts specific symbolic properties. We're talking about shape, color, size, position, and things like rotational or reflective symmetry. By extracting these, the system stops looking at the whole grid as one big visual structure and instead creates a compact, object-centric intermediate language. Every detected object gets a canonical representation, which lets the reasoning engine start manipulating actual concepts rather than just fussing over absolute pixel positions. To give you a concrete idea of why this matters, take a look at this task pulled straight from the ARC training data. The input has these incomplete 3-cell L shapes. Because of this object-centric shift, the system doesn't just see a grid of colors. It actually recognizes a broken shape, identifies the missing component, and realizes it needs to be transformed into a complete 2x2 square. It moves from global spatial guessing to precise shape abstraction. Let's open the doors to the engine room for section 3, the GLYPHBLOCK runtime engine, the governed state machine. This is the formal execution environment, and it is entirely controlled. The solver doesn't just arbitrarily jump around. It starts with these first 4 explicit reasoning stages: perceive, abstract, hypothesize, and compete. And this is exactly what sets it apart from your typical, opaque, end-to-end LLM prediction. The system makes the reasoning pipeline totally explicit. It generates multiple hypotheses about a transformation and actually forces those hypotheses to compete against each other. And here is the second half of that governed pipeline: synthesize, execute, verify, and prove. After those hypotheses battle it out, the surviving logic is synthesized into a program, executed against the training examples, strictly verified, and then mathematically proven. Every single transition is deterministic. It leaves a clear, auditable trail. That takes us to section 4, program synthesis and competition, basically a survival of the fittest for logic. Now remember that competition stage? It's absolutely crucial because the very first plausible interpretation the system comes up with is usually visually appealing, but logically completely wrong. Say the system spots some missing colors, its first hypothesis might be way too broad, something like just add color to every adjacent cell. When it executes that against the training examples, it fails, so it gets rejected. But a second hypothesis, like complete every 3-cell L shape, survives the training examples. It eliminates the bad guesses by treating hypotheses as executable programs. And where do these programs come from? Well, rather than treating every single puzzle like it's a completely unique unicorn, the architecture searches a library of reusable symbolic primitives. It's essentially reaching into a toolbox of modular blocks. It pulls out simple operations like region mapping, object completion, reflection, or rotation, and tries to combine them. So the goal here is to find the most appropriate executable program that explains the examples. It builds these blocks into a pipeline, maybe it detects objects, completes them, reflects them, merges the result, and then verifies. It's literally searching for compositional logic. Now, this doesn't mean it always finds the mathematically optimal program every single time, but it builds a working logical sequence that generalizes to the unseen case. Which brings us to the climax of the system in Section 5. The exact verification gate. No fuzzy success. This is one of the framework's defining principles, and it acts as a massive guardrail against overfitting. We're talking about a strictly deterministic computational gate. There is zero room for semantic similarity. There is no visual approximation. The difference between the predicted output and the expected output has to be exactly zero. If a single pixel is wrong, it fails. There's no close enough. So if it gets an exact match, the program is accepted. But if there is any mismatch, the gate rejects it. And it doesn't just guess again. That unforgiving gate forces the system back to an earlier computational state in the governed machine. It has to refine its abstraction or synthesis. This prevents the system from confidently spitting out visually plausible but logically broken transformations. Finally, let's zoom out for Section 6, Achieving True Generalization, and look at the three-layer architecture. This is how it all integrates with the official ARC AGI toolkit. Solving these static grids, that's really just layer 1. Layer 2 is where it searches and composes those complex programs. But layer 3 is where this gets wildly ambitious. This is where the solver connects to the ARC3 agent environment. The system moves from static grids to dynamic interaction, exploring an unfamiliar space, figuring out the mechanics, building a world model, and dynamically planning its actions based on this symbolic reasoning. This entire framework really just proves that we can build inspectable, deterministic laboratories for machine thought. By forcing a system to explicitly extract objects, generate competing hypotheses, compose modular programs, and survive that brutal exact verification, we fundamentally shift what AI is doing. We stop asking our machines to just regurgitate what they've seen, and we demand they deduce the actual mechanics of their environment. So taking this journey from pixels to programs leaves us with one massive, lingering thought. Just how far can this compositional logic scale before these systems start discovering rules about the world that we haven't even figured out yet?